No. Change on online. In or post. Welcome. Alright, so welcome. Problem set 10. Week 11. So it's just 1 week left. Woo! Or depends. So today we're going to look at a new programming language called Prolog. What's different from Prolog and the other programming languages we've seen before is that this is an entirely different paradigm. So we've seen object-oriented paradigms. So if you think of it as like 3 pillars, you have the object-oriented paradigm, where everything is an object and you can manipulate them as objects, and that's what you're familiar with. Then you have the functional paradigm, where like functions are the only thing that really matter. Like you don't have any objects, and you can pass functions around and do everything. Like the functions are like first-class citizens. Now the third paradigm is the logic paradigm. And Prolog is like one of the languages that like brought that to the consumer, if you want. So my first question is like, what's different between the paradigms? Like, what's the difference between the logic paradigm and the object-oriented or functional paradigms? Well, maybe I'll just paint. I usually have a drawboard, but I don't have it because I have to draw for the students that are here. So you'll have to see my awesome paint skills. So if you think about it, I have like here I have like object oriented. Okay. So I have like func, which is the functional programming. And then I have the third pillar, which is logic. And like, wait. Okay. So, oh Jesus. Okay. Functional. And as I said, you just have to. Okay. Oh, come on. Logic. Okay. So you have these like 3 paradigms, and they all can overlap. But the interesting thing is that between them, like you have languages that are overlapping between them. But the logic part is like, I would say like most separated of them. So okay, back to like what's the difference? You think about how you program in functional programming or object-oriented programming. You're always instructing how to do stuff, like do a for loop here, iterate over the list, do this, do that, like, and you're doing like you're declaring how to do things. But in logic, you explain like how things should work, but you don't actually do the work yourself. You just tell relations between something, and the programming language itself figures out the answer for you. So that's kind of new. So if we jump to this thing here, wait, I have it. Notepad. You've seen it all. Okay. Can I just maybe do this and then jump back? Okay. So let's just. So when I say like a programming language figures out for you, what I mean is that the only thing you do is you specify something that you define as true. Like you state facts. Okay. So if you know something for a fact, you give a relation that's just fact, and he can use those facts to fact check, if you want, to find the answers for you. Okay. Now this is all really high level. Let's bring it down to actual code. For example, if I say like is empty, and I say okay, this is an empty array. Oh, here you go. So this thing, okay. And when I say okay, this is basically defining a fact. It's saying, well, this fact says that this name is empty. It's true when I give it the empty list. Okay, and how I run it, it's like this, and I say here is empty. It says true, and if I give it something else, it says false. So okay, this isn't that interesting. It's just like a one fact. But if we define something that he can actually work with, let's start with the first assignment. Even. Wait, I'm gonna back up a bit because like I think I'm going in a circle here. Okay. Basically, Prolog, every statement that you declare is true. Everything else is false. So he uses your rules to figure out the solutions to your questions. Okay. Now you ask by like querying the things that you're doing. So for example, this you can think of this like in SQL. You know SQL, like the database thing, where you can say like I want this data. I specify how the data should look. I don't care how you find it. Just do it for me. So here I'm saying, give me something that is like I define how the shape of the data should look like, and you find it for me. For example, if I say is empty, and I say empty, and I say, well, I don't know the parameter. Just figure it out on your own. He says, yes, I found it. It is. X is empty. This is the only solution that I found. You see? And I didn't actually, I didn't tell him that this is true, like, in the query itself. He just found it out himself from the facts that I told him. Okay? So, okay. So everything that you specify is true, everything else is false, so he uses your rules to figure out what applies. So every parameter that you, pick into it, he uses and checks if that if he can verify any possible solution from that parameter and gives you all the possible that are actually valid solutions. If that helps a bit. Oh wait, I have to check if I get any comments on the live chat. Live chat, no one here. Okay. Alright, so let's head out to the first assignment and check if we can do it. Okay, even. This is something that takes in a list and returns if the list is of even length. Now, in normal, I would say normal, like in object-oriented or in functional programming, you would just say length modulus 2 equals 0, and you're done. But that's the way of saying how to do it instead of saying how it should look like, or the data you want. So for example, in Prolog, you can say, okay, even, is it called? Yeah, even, and empty is definitely even. So I say even, empty, true. So that's stating that the empty list is definitely even, right? Okay. Then I say, okay, but it can also be that it's not empty, it has to be something else. Well, then it has to have at least 2 elements, then the rest of the list. Now, Prolog is also very, very excellent in pattern matching. So what you can do, you remember in ML, you can do something like this, like head, ::t for tail. Well, Prolog has actually a better syntax, from what I think. Okay, you can say give me 2 elements, I don't care what they look like, and the rest is t. So here you're actually indexing 2 elements, saying there are 2 elements, and t is the rest of the list, this holds true if I recursively call t again uneven. Now, what I'm saying here is like, this is true if this holds. It's just like a logic statement saying like, okay, the thing that I described is true if the following thing holds. Okay? So what happens here is that the pattern matching takes the list that I'm looking at and says, okay, you have to have two elements, at least two elements, and something else, like the rest of the list, doesn't matter. And then it says, okay, I'll take the rest of the list and ignore the two elements and call myself again. See how the recursion is doing. So it's good to have looked at functional programming before looking at Prolog, because Prolog actually uses recursion as well. Like really, you have to get into the side of recursion. All right, shall we try it? Shall we try using this? I recommend that you download Prolog SVI, this thing. It was a bit of a hassle, but you can actually, if you take it out, you can actually do this. Like, this loads the file that I'm working in. So this is the file that I'm loading here. And every time I load, he says like, true, I managed to load the things that you told me to load. So if I go even and say, okay, is this array even? Yes. Is this array even? It says no. Is this array even? Yes. Okay. Or give me an array that's even. This is even. This is even. Okay. So what I'm doing now is that I'm saying, okay, I'm calling even and giving it a variable, saying, I don't know what's true. Tell me what holds true for this relation. Okay. So he says, okay, I'll take the x and I'll try to find every solution that fits the x. Right? So the first solution he found is the empty. He says, yep, empty list fulfills this relation. Like, it's true in this thing, right? Because I just told him to. Okay? The next thing, the underscore number thing, that's just saying two wildcards. There are two things that it doesn't matter what is there. So he's just giving us like random numbers because he doesn't know what value should be there. You can think of them like a question mark. There are just some values. But you can see this actually fits. There are two values in the array. The array has an even length. And how you get the next result is by pressing the semicolon. And you get the next result. So you can see the next result he found out is like, I have a 4-value array. And then next result would be 6-value array. He found he just checks and checks and checks, and he finds every solution. So if I hold this down, you see I get really on. So when you finish, you press plot, and he's like, okay, cool. But you see the power in this, compared to the functional or the object-oriented, that this really simple code, I managed to get every permutation to. I got every solution for an even length array. Every solution. It's cool, right? Okay, let's move on. So is this clear? The even part. Okay. No questions here. Okay, my last. This function, or this relation, as it's called in Prolog, checks if the x is the last element of L. I'm going to do that as well. Just going to do it, and I think you just follow. And the next one, I'll ask you how you would do it. But they get quite difficult, they wrap up. But let's do this. I'll do this one, and you'll help me with the next one. Deal? Right. So I have my last, which is the x and list. So I have to check, is the x the last element of the list? Well, the base case for it would really be just to say like, well, if I get an X and an array with one element in it, well, that array has to have the X in it, right? It's the last element of the array, since it's only one element in it. Therefore, I can do the pattern matching. You see the power of the pattern match in Prolog. Here I have an X, which is just the parameter I have on the left side. And here I have an array with that X. See, they're exactly the same X. And that's how he uses the pattern matching. You can see he just takes the X and says, oh, okay, I have to have an array containing that X. Like this, the same X, the same thing. So this is just saying I have to have, okay, my last is true. The first argument is the only element in the one element list in the second argument. It sounds really complicated, but if you look at it, I think you can look at it. But basically, these two X are the same. It's just using pattern matching to match these things together, and this is how it works. Okay. Next. So, okay, since the list can be of whatever length, we need to like recurse down it. Does that make sense? Like we have to get to the bottom of the list to actually evaluate that the last element of the list is indeed the X that we got. So my last X dot. Now here the pattern matching also helps us. We say wildcard underscore is a wildcard saying any element, doesn't matter. I don't care what element, T, and here I say, okay, what I'm doing here is basically I'm taking and saying I'll take the first element of the list, ignore it, take the rest of the list and do something with it. Okay? So I'll say my last of X T. So like this relation, like this fact or relation, only holds true if the rest of the list satisfies my last. You see? Do you see how it recursively goes down the list until it hits the base case, which is the first fact that we set? Does it make sense?
What about after the second parameter?
Yeah. This thing? No. This thing. This thing again. Right. So what I'm doing. So if you think about how ML does it, it was like HTTP for head and tail. Remember? That was like the ML way of doing it. So like this is ML and Prolog. Do it this way. Say, okay, I have an array, and I say head pipe T. This is just the pipe is saying after the pipe I want the rest of the list. However, in Prolog, it's even more clever than ML because you can actually specify, well, like I want like two elements, or like go like this. X, Y, then I want the tail of the list. I'm getting like the first two elements and then the rest of the list in the tail. But in ML you had to say like car of coulter of like list. Car of coulter like you remember. So like wildcard is just saying like I want wildcard is like ignoring the variable. Well, if you actually designate a variable for it, you can actually use it on the right-hand side of the expression. So, if, for example, I can't use this wildcard here. If I do something like this, then this wildcard and this wildcard are not the same thing. So it's not, you can't match between the wildcards because wildcard is you telling Prolog that you don't care about it. Okay, yeah, cool. Right, we are back to all but last. So this relation should tell us that L1 and L2 are exactly the same, except the last character in L2 is not present in L1. Does that make sense? So like list L2 contains all but the last element of list L1. Oh, wait, like the opposite? Okay, it was the opposite. But it doesn't really matter which way we go. So, first thing we should do is let's use recursion, since we already got we have a bit of recursion here, and we've done a lot of recursion before. So, how would we do this? We somehow have to split up the array and do some stuff. Okay. So, all but last. So, let's say, what's the base case? Should be checking if, like, let's say that this is empty. What happens then? Should they both be empty? Is that true? To the tail, or at least one element. Exactly, one element. So I say, okay, this is true if the first list is empty and the second list contains one element. I don't care what the element is, it just has one element. You see, the wildcard helped me there. So this is true because then I'm saying, oh wait, list L1 contains all but the last element of L2. So it should be the other way around, right? Like so? Does that make sense based on the description here?
Yeah.
Okay. Well, either way. Okay, so like this is the first the first case. What's the next case? Oh wait, I forgot to actually run my last. Oh my god. Why didn't no one tell me? Okay, we're gonna take a quick detour and run this. All in favor, say aye. Aye. Okay, my last. No, wait. I need to refresh and then call my last of x. Oh wait, x is just a. And we'd say, okay, we have some list and say like E, C, D, A. This should be true, right? So it's just checking that the thing you got in is the last element of the array that you got in as well. This is true, right? Make sense? Is it too tiny or? Fine, okay. Okay, however, what happens if I do this? Should this be true? Nope, should not be true. Exactly. However, whoa, Jesus. Okay. However, what happens if I do this? What should he return? X equals D. Woo. So, like what he does is gives me x equals D, and when I say give me more solutions, he says false because there are no more solutions. Okay. So what happens if I do A and do X here? What's this? So what happens is that he checks and says, okay, X is satisfied if A is inside the array as the last index. And the first case is when it's the only element in the list. And if I do give me more, he just says, okay, I have something else, and then A. Give me more. Something two else, then A. So all of this are satisfied by my last query. You see how Prolog is? It's like a query language that you describe some facts, and then you can query any parameter in the space. Really powerful stuff, right? Okay. So that was basically my last. Any questions about that before we continue again? Oh man. Alright, so no. Yep, no one's talking. Can I see how many are watching? Like live? Is that something that you can do? Oh well, it doesn't matter. Alright. Okay. So back to all but last. For me, I have it on my phone. Okay, so all but last, let's get back into it. So all but last, here we go. We have to declare somehow recursively getting down to it. Okay, so here I would say let's try to split the list into two things, and let's look at, for example, like two lists that satisfy this relation. Okay, let's say A, B, C, D. These two lists satisfy the relation, you see? And what's common between them? Every index, like in stepwise order, they're exactly identical, right? It's A and A, then it's B and B, it's C and C, and then something else. You see? So if you think about it, every index here is exactly the same except the last one. So that's basically what we need to do. We need to check that L1 contains every element. Wait. Boom, boom. Okay. We need to check that L1 contains L1 and L2 have the exact same element up until the last element. So how would you do that? Let's say we split both of the lists. So I have these two lists. I say here's tail one, here's head one, here's tail. Oh wait. Here's tail one, here's head two, and tail two. Sorry. And here's head one. Okay. So my question is, what is head one and head two? Aren't those should be identical, right? So we could just use the pattern matching and say, well, they should be identical. The head of this list should be the same as the head of this list. See the pattern matching at work here? It's powerful stuff. But you know that T1 and T2 can't be the same because they have different endings. At least one different ending. So you can't say T and T. Okay. So this is true if what? So I just have to recursively call myself again, right? Just with T2 and T1. So I say all but last T1 T2. Okay. See how it's going? Like, I use the pattern matching to check that these two elements are the exact same thing. Then I grab the tail of the first list and the tail of the second list and call myself with the tails. So this would basically recurse down to this point, and at that point he would say, oh well, here's an element, and here's one element, while the other is no elements. That's okay. So let's try to use this. So wait. Now we have to go here and say. Okay. Need to reload because I just saved. I say here all dot last and give it some parameters. So what did I have? Like A, B, C, and then I had A, B, C. Oh wait, it was A, B, C, D here, right? Like this list should be one extra. And this basically is the question, like, is this true? He says, yep, it's true. And then my question is like, okay, what is this? Right, doesn't make sense. So x should be equal to ABC. Because what he does is says, okay, I use the facts and see what satisfies x. And the only thing that satisfies x is this thing. See, like, once again, like, Prolog is really powerful. Like, you can ask any, like, about any parameter, you can ask any question. Like, give me solutions given this and that. So, what should happen now? I don't know. Basically, saying that like more solutions is like any, and you say like here they're doing exactly the same. Like these things should be the same. Here these things should be the same. This thing should be the same. So you can see how the pattern goes, but wait. Oh, here. Alright. Any questions about this? Like we're getting into more heavy stuff now. But I think like once you get the get the hang of it, like it's still pretty hard to like wrap your head around another concept of writing code. Like this is totally different coding style than what you've seen before, but it's cool. Right. So the next thing we should do is called myLength, and here something interesting happens. N is the length of the list. Now, what you would do is just say, well, in a like object-oriented or functional programming, you would say like, well, L.count or L.length. Then, but now we have to actually count. Or you would have some array that looped over it and checked. Okay, so myLength. So we have this list, and we can say, if it's empty, well, it should be 0. Does that make sense? That's a fact. Empty array is of length 0. However, if it's not empty, then I have to do something. Here comes the tricky part, or at least a new part in Prolog. So let's say I have this thing, and I'm gonna take the head of it. I'm totally gonna ignore it because I'm not looking at the content of the list. I'm just looking at the list itself, just counting them. So I'm gonna take the head and get the tail. So that's just one element. Okay. I'm gonna say n here. This holds true. Where's 0? This holds true if my length of t and n1 holds. Here comes the new part. Comma means and. This has to be true, and this has to be true. Nothing that's on this side. This is just like putting amper or something in like normal programming languages. Just comma means and. So in order to satisfy this thing, both of the clauses here have to be satisfied. So what's the second clause? Well, you can say, let's say n is n1 plus 1. So you can see what's happening here. I'm gonna break this into like 2 lines because it's fun. So this has to be satisfied, and this has to be satisfied. And you can see, like here I'm saying n is n1 plus 1. Now, before I run this, there's something that you need to know about Prolog. The reason why I can't just say like x equals 2 equals 1 plus 1. What do you think comes out of this? True, of course. However, false. Now the reason is, when Prolog sees this sentence, he says, well, 2 is not 1 plus 1, the 3-letter thing. You see, it's not identically the same thing. It's not like saying 1 is, but is it the same? Yes. So what happens is basically the other is just checking like absolutely identical versus I'll evaluate both expressions and then give you if they are the same eventually. Like
3 plus 2 is 2.
yeah, so 2 equals 2. Right, true. So 2 equals 2. True. But 2 equals 1 plus 1 is definitely not true. But 2 is 1 plus 1, that's true. So that's something to keep in mind when you're like tearing your hairs out in the next programming assignment, is you have to think about this. Okay. Something I fouled on. Like I forgot to think about this when I did my assignment, and I was like, what's happening? Alright, so here we go. So let's take this expression. We have to reload, right? So reload. So that's the reason why I say is here instead of equals. Reload. Here we go. Okay. My length of let's start with the easy case. So this should always be true. Okay. This should be what? Easy questions. No trick questions. 0, right? Hey, 0. Right. So let's do something interesting. Let's see if I say like 1, 2, 3, next. What should this be? If I did it correctly, it should be something that's really familiar. Great. Length 3. No, the second parameter is the length of the array. So if I say like 3, it should be true. And if I say, well, x here, what will be true? Like, what's x? So you always have to think about like what value of x will make this expression true. So that's what he's asking himself. Like, yeah, wildcard in the array. So 3 wildcard array. There you go. No other. Wait, I'll ask him for another solution, and he'll run indefinitely, because, well, he's checking and doesn't really know. And maybe I can. I don't know how to break the. So you have to, like, in Prolog, he uses your rules to check, like, okay, if you think about it, like, he starts in the most simple case as he can, and then he does like a search, if you think about it, through the state space, or through all the possible solutions that are available. Well, if the possible solutions are infinite, then he'll do an infinite search, unless he can prove to himself that it isn't infinitely long, the state space. So that's the reason he actually just failed. But he gave us a solution. Like, he gave us a solution really fast, though. So, does that make sense? Right, next element. It's elementary, dear one. Okay. So, element X is an element of list L. We can do it like this. How would you do this? It's like saying, well, X is in the list L. And now I'm gonna stop helping, or reduce the help. Okay? X and X, like so. Well, the L is a list, see? So you would have to put it in some kind of list. So this is definitely true. However, like, we can do it even better. Okay, let's stick to this one. What's the other case? So we have the base case. It's saying, okay, well, if it's the only index in our array, well, then it's definitely in the array, right? So our task is to find or check if X is inside of L. So, like, think about it, this is L. So what happens if we don't find it? Like, let's say we have, this is Y, so something totally different than X. Okay? What happens now? Let's say this. This is the hint I will give you. What now? See what I'm doing? I'm just saying, okay, well, X, I got X in. Well, the first element in the list is definitely not X, sorry. Therefore, I'm gonna do something.
So the element X, comma, welcome, T. No, just
Here we go. Just T, the tail of the list. Cool. Yeah, that's true. However, okay, so do you think this is
probably not.
probably not? Okay, I'll give you an example why it's not that good. Okay, say they have A, or why it's not perfect. So A, B, C. Like so. Does this hold true?
Yeah.
Of course. Does this hold true for the thing that we described? The first thing that happens here is that we get X in, which is B, okay? And we'd say, okay, so I'll do this, okay? Okay, we get B in, and this is A in the beginning, and tail is BC. It's hopefully not confusing, but this is the first case, right? Okay. What happens is we follow this rule, and that brings us down to, oh wait, not B, small b, sorry. That brings us to, okay, this thing calls this again, and it says, well, we have B on the line. However, B is not the only element, like here. Like, we have some lists here afterwards.
So the base case
Yeah.
would be 5.
Yes, there we go. Exactly. So the base case now says, well, I found an element that is X. I don't care if the list continues. I found it. And voila, I'm done. Hope the genie dynamic helped. Okay, so shall we try this? Oh, wait. Wait, what are we doing? There we go. Oh. Okay. Oh. The color. Okay. Okay, wait. I'm gonna reload my thing. There we go. Element of, well, let's try the thing that I just described. I got E, A, B, C. True. Yes. So that's true. So is this true? Nope, it's false. What about, do this again, like B and C, and do X here. What do you think X will be? What values of X satisfy this relation?
All of them.
All of them. So A, B, and C. So it's A, B, and C. Nothing else. So that's pretty cool. He actually figured out that these are the only elements that can fulfill the thing. Is it cool? It's cool. Yes. Okay. Alright, so wait. Here we go. So the next question is, wait, before we go into that, what is, just one more quick question. What is this? What would be the first thing you see? When I press enter, what happens?
List with A.
A list with only one element, and that's A. Well, it's kind of true, because a wildcard can be, yeah. So, like, yes, it's true. Alright, so, let's continue. We got subset. Do we have any more questions on the element? No? Alright, subset says every element of list X occurs in list Y. So how would you do that? So we have two lists, X and Y. So what happens, what's the base case? What do you think would the base case be?
The two lists.
Two lists?
X and
So two lists, X, X. Oh wait. Okay, let's say A and A, because X is. Oh wait, sorry, you mean like actual, like the same characters. Okay. All right. So what's next? Hint, hint. We just created something called element. So okay, let's take another into like two lists with a head and tail. We have like a head one and tail one, and we have another list which has, or you can just call it list 2. Okay. What we can then say is okay, what we can then use element. We can use element on the head of this list on L2. Does that make sense? So the first element in the first list has to be an element in the second list. Right? And here comes the dot, like comma, and what?
Element with head 2.
Element with head 2.
Tail 1. That is 1.
2. There's no head 2. We've already, okay, we've shown that like this holds. Then if this holds, we have to continue searching, right? Like if the first element in this list does not hold true, then we don't have to search. Well, the next element, or we use subset here. So basically, subset takes T1, the tail of the list, because we've already proven that the first element is in L2, then the rest of the list has to be as well, and L2. Does it make sense? Now, the base case can be better. Okay. So, like this, okay, let's just look at this for a second, like, just to make sure that we get it. Okay. Okay, so what I'm doing here is that I say, okay, we'll take the first list, split it into head and tail, right? And we'll leave the second list just intact. What I'm going to do, I'm going to say the head of the first list must be an element of the second list. That's what this statement does. It must be an element of the second list, all right? And if that's true, well, the rest of the first list has to go subset as well in L2. You see how I break it up? I take the first element, check that it's an element in the second list, then I ignore it and continue on with the rest of the lists doing the same cycle. Like, here's the recursive call to myself. And well, the base case is actually, if I have an empty list, well, empty list has no element, and therefore it's a subset of every list, right? Every list has a subset of nothing, right? Does that make sense? So, like, if I have an empty list, then it doesn't matter what I have here because it will be a subset. Make sense? Okay, let's try it. Ignore all the errors. Okay, I've just reloaded, and now let's do subset. subset of, let's see, so we have this list A, B, it's just the A, B, and then we have to say, okay, A, B, okay, A, C, D, B, so like this. So this would be what? True or false?
True.
True. Okay, cool. Wait, what? True. There we go. Right, so should this be true? Of course not. Right, so, well, should this, another silly example, this would be true. Oh, alright, what about, wait, what about do A, B, C, D, or just like A, B, C, and X here? What's this? What X satisfy this relation?
A, B,
A, B, C? But now we have to think about, like, isn't it the empty list as well? Because the empty list is included in every list, and then we have to have every permutation of one element. Good. Yeah, okay, we'll never get to the B and C's because, well, A is always a subset. But yeah, you're right. So like X is also B, and X is also C, and X can also be AP or PC or APC, like any of the 3 or 4. We'll never get to it though. Okay, what about if we do maybe it's not too harsh. If we do X here. Wait, if I tell it and it's supposed to be a 1-element array with X, and then I say A, B, C. Second element. What should this return?
B, A, B, C.
A, B, oh wait, oh. A, B, C, false. Empty, yeah, of course not, because you can't have an empty, like, A, B, C. So you can see how powerful this is. It's just, I'm actually, like, in a really compact form, asking a really, like try to do this in, like, what is this, like 2 lines in any other programming language. I challenge you. But yeah, it's a really powerful thing though. Okay, let's continue. Right. Element at. So we're down to this thing. So this is basically X is the kth element of list L. We assume K is equal or greater than 1. Okay. So we have this X, which is some element. We have this list, which is L. And then we have this K. The K is just the index where X is in the L. So how would you do this? What would you say? Let's take, for example, this case. Looking for an A, I have this list, A, B, C. What would the K be? 1, right? That's because we have the restriction that K has to be 1 or greater. Okay, so 1. So this case sounds pretty good. Let's try to model. Let's try to like put it into code. So elements at, and then we have an X. Then first index of the array that we have, L, should be X, and the tail doesn't really matter. And this should be 1 then, right? because this is the first index of the thing. See, we just took this and used pattern recognition, like we used pattern matching to map it to this. Right? Okay. So now we got like the base case. We got that. Nice. All right. So what's next? We have to like iterate into the array. So let's break this array into. Let's break this array up again and say t here. So we're ignoring the element themselves. They don't matter. Like we just get the tail. And now we can use the same procedure that we did last time. That we can ignore the element, continue, and say k plus 1, and then we crystally call ourselves. I think I'm going too fast. Yes. Yes. Right. How would you do this? So, before I continue, did everyone get this? Why I have this up? Okay, I have an element here. Like I'm looking for this element. Well, if that element is the first index of the list, then I should return 1. You can think of it that way. Right? It doesn't matter what's the rest of the list. It only matters that the head of the list is the same as the thing that I'm looking for. Okay? Follow? Okay. So let's look at a list that, for example, this list A, B, C, D, usually A, D. So this should be like something like 2 or 3 or something. 3? 1, 2, 3, yeah, 3. Okay. Now, what we want to do is that, well, this starts out being something like this starts out being like this, and then we want to recurse and remove, like at every step, remove this and remove that, and then find this and hit this base case. Does that make sense? We like recurse down, remove the B, remove the C, and then say, whoa, we got A. That meets this case. And once we get out of the recursion, we like add the case together. I think I'm still going too fast. Okay. So what I'm saying is that what we can do is we can say, well, we'll call ourselves again with DAX and the tail of the list and K1. Okay. And now again, the K1 is the same thing. Like, sorry, here we go. K1 is K plus 1. Wait, isn't the other way around? K is K1 plus 1. Like so. Does it make sense?
Yeah.
And you see how he accumulates the pluses. Like it goes down to the base case, gets the 1, and then every step A up, he increments by 1. Alright. So let's see if this works. So any questions about this? I know it's a bit complicated. Welcome!
Thank you.
Oh, Jesus! Oh yeah, I copy-pasted the wrong thing. Ignore the errors. Okay. Alright. Element at. And then we have this. Okay, let's do the thing that I said just before. I said like A, and then I got the B, C, D, or A, D. Here we go. And it's a 3, right? Hey, it's true. Okay. So next thing, maybe I'll make this a little bit bigger. It is kind of small. What? Okay. Columbia. Okay, this is true. I think it's still as small. Okay. So what happens if I say X here?
Not found.
Element not found. It's A. Because he says, okay, what he does, he says, okay, what values of X satisfy this relation? And he just checks, well, I'll look for number 3 in the array, and that value is A. Yes?
Does X have to be uppercase? It can't be low.
Oh, X uppercase means that it's a variable that he will figure out on his own. Like a lowercase thing is like constants, if you think.
So if you try to put a lowercase x, what will it do?
I think he'll say false because X isn't at third position in the array. All right. Here's another thing, like X, Y. What should this be? Let's see how Prolog is powerful. He actually will tell you, well, the first index is B, the second index is C, the third index is A. Just find what satisfies the relation at every step. So this is the first example. You see that I have 2 variables and he's trying to satisfy both of them at the same time. And he does that excellently. Right. Cool. All right, so there. So the next thing up above is element. So we are here. Insert element. So I really encourage you to try out at least try out the first 3 examples on your own, so you get the feeling. So you're just not looking at me and say, "Yeah, that's totally simple." All right. So element, insert element. So what should this be? So it takes like X and puts it into L1, and you get the L2. Now, the trick is that you can place it anywhere in the L1. So for example, if I have 2 lists, like let's say this is L1 and this is L2, then you have, for example, like A, B, C, and you have like A, B, E, B, C, and you have the X being B. This is totally valid, right? Because you inserted D here, but this is also valid as well, because you inserted it there. Like, you can insert the D anywhere you want, and it's still valid. It's not saying that where you're going to insert it. It just says, well, let's say we insert this value into an array. Will I get this array back? So we got X, we got L1 and L2. How would we do this? And notice, if you notice the pattern here, is that, well, before we actually reach the element that we inserted, how do the lists look? Oh my god. There we go. They look identical, right? Like every element of the lists are identical up to the point that you insert it, and then after the point, they look identical. So if I would insert like more elements here, if you see G, F, something, it would also look identical. So that's something we can use in our pattern recognition, like the pattern, when we are using the pattern system in the Prolog, which is excellent. Okay, so we can use that, like, the first part is the same, the last part is the same, the only difference is this guy. Make sense? Okay, so what we're going to do is we're going to say, well, if we have an empty array, then, well, we have to have x here, right? So, like, the first array is empty, the second array contains only x. That makes sense? But that's basically taking this case. You see? This case. We're just saying that if we have an empty array, then the second array has to contain the x. Only the x, nothing else. But if we'd say, well, these two parts have to be identical after the x is found, then you can use the pattern and say, well, we have here L1, and the rest of this thing should be L1. Does that make sense? So, like if I have this list, these two lists, I have the list A, B, C, and the list B, C, and I got like A as an input. You see what I'm doing? I'm taking, wait, it's the other way around. Sorry. It's here. Okay. I'm taking the first element, or I'm taking the first list and saying, well, the first list should be exactly the same as the rest of the second list. If the first parameters are, like, if the thing that I got in is the first element of the second list, then the tail of that list should be the same as the first list. You see? Like if you read this. That's what I'm trying to say. Probably fairly. I feel like I've lost you. Yeah. Okay. Well, okay, let's try to back up a bit. Okay, so the task at hand is basically you have like 3 arguments. The first is an element, and the second 2 are lists. Okay? Now, what should be true about this relation is that if you insert the element into the second list, then both of the lists are identical, but the second list has this extra element in it. Right? So you can see if you look at these 2 lists, they are identical except for this one extra element. Now, the trick about this question is that if I exclude this thing, I can basically put it anywhere. I can put it in the front, I can put it on the second index, I can put it at the back. I can put this element anywhere. So the task is basically getting running through both of the lists, identifying that the head of the lists are the same until you hit the point where this element is in one of the lists but not in the other. And once that point is reached, then you know for a fact the rest of the lists have to be identical, because the only difference is that element. The only difference is that element. So if I would remove that element, the list should be identical. Okay, so that's basically the task that we should try to program in Prolog. Now, the base case, which I've set up here, is basically taking the fact that we know that the end of both of the lists should be identical, which means that if we get a list, in where the head of the second list is a is the thing that we're looking for, well, the rest of the list should be identical to the first list. Lost you?
No.
So we're using the power here of pattern recognition, because this is pattern matching. Sorry, because here you're actually like using like a really compact sentence is explaining a lot of stuff. Like a lot of stuff. Like I'm saying, well, I'm going to get X in, and the X should be the first element of the second list. And if that's true, well, take the first list and the rest of the second list, and they should be identical. And if that's true, it's a fact. So it's like in one sentence, you're doing like 5 different things. But it's totally cool. All right. So once we're done with the base step, which is just checking the tail of the lists, we have to check the front of the lists. And when we're walking through the front of the list, we need to make sure that the head of both the lists are identical, since they are not X yet. So for example, in this example, like if we're just walking over the list, we should say, well, head of L1 and head of L2 should be the same, okay? And here also should be the same. And once we hit this case where they're not the same, well, this case should cover it, okay? And if it doesn't cover it, well, it's not true. Like, it's not true that those lists are indeed satisfying the relation. Okay, so how would we take the first part? Well, what we would do is basically say, I have a head of some list, and I'll call it T1. I have a head on the second list, and they have to be identical. Like, these two elements, like this head and this head, have to be the same. Because the lists are identical up to the point of the insert. So if this is true, well, then I'm gonna say, like, this is true, and I'm gonna recursively call myself again. Insert element at x dot t1 t2. That's it. So what you're doing is basically you're matching that the fronts of the list are the same up to the point where you hit the case where you inserted the x. And if that's true, then the rest of the list should be the same. And you can do that really powerfully by saying, like, match this list to that list. So this is literally, this is all the code that you need. Oh wait, let's just have it that way. Okay. So let's reload and try to. Oh, it's not true. What's happening? What did I do wrong? Yeah, that's right. I forgot to save. That's what I did wrong. Okay. So I say here, if I say insert element x dot, or so what were the cases that I had before? Let's go back. See them. So I had this case. I had a d dot, and the first array was like so: A, B, C, D, F. Okay. The second array was A, B, P, because the D inserted thing, C, D, F. Oh. True. Okay, this is true. Now my question is, let's try to reduce this a bit. And let's say, I'm going to say A, and here's going to go B dot C. And here's going to go to X. What what is X? So the intuitive question is like, what values of X satisfy this relation?
ABC.
ABC, that's definitely one case. What else? Remember, you can insert element at any position in the array.
PAC.
Exactly. PAC. PCA. That's all. So you can see like every permutation he actually finds. It's cool. It's cool. Cool. Very cool. So let's do another. So I do this and I say, oh, wait. Yeah, okay, same. Sure. So I'm just saying, like, if I get any wildcard, he'll put the wildcard into these three positions. That's what he's saying. The same with the A as above. So if I do, wait, A, B, C, wait, do this. What should this be? Well, if I put, wait. Does this make sense? Mm-hmm. All right. Well, so we have 5 minutes. Maybe I can go. I think I can pick the next thing, but maybe we should just go back and you can ask questions if you want. Like, is this? Maybe it's not like. Probably have to do it like in your fingers as well, but hope it's helped. Right, so I'll just continue with the next one. Right? Yeah, nice. Okay, occurrences. So, occurrences. So let's say element occurs n times in the list L. So I would say X occurs n times in L. So the first thing we would do is say, okay, well, I would guess the base case was that if I got an empty list and I got an X, I should get a 0, right? Because X occurs 0 times in the empty list. Okay. So the next thing would be, okay, I have this n here. Well, if I got an X and a tail, well, we should increment n by 1. Does that make sense? Yeah, I think so. Alright, so I would say all occurrences of X dot. Wait. We need still, sorry, T and N2. Okay, so that's just recursively calling ourselves. The reason I said I put N2 there, should I step back?
Oh.
Okay. Okay, the reason I put N2 there is because, well, we have to increment N. So here I would say N is N2, oh, N2, wait, which one? Which way? Plus 1. We'll figure it out. If it's wrong, we'll figure it out once we run. So wait, other occurrences, so like 0, this is true. Okay, this is the way you should do it. So, so this is one case. Well, the next case, and here comes this, like the third fact we do. We only done like 2 facts this time. Like we done the base case and the step case that actually like does the logic of recursing down the thing. But now we have three cases. You see, we have the case of we actually found the match and then we have to increment it. But what happens if we do not find the match? Well, then you have to not increment it. just call it with itself. There you go. You see? So maybe I should do like so. So now okay, to be more exact, you can do this. And you would have to say x, I think it's like not x, y, comma. And that's basically saying, well, we're guaranteeing that they are not the same thing. Because this case should cover that thing. But here I might run into a syntax error because I'm not really sure if it's correctly syntactically right. Right? Syntax error. What's he on about? Line 44. Basically, if you don't use the variable, you'll save. Remember to save. There you go. So what he did there, he was complaining that I had an x here. The reason is that I don't use the x anywhere. So he's just saying, well, I won't compile unless you specify that you're not going to use this variable. And if you're not going to use it, then you should specify a wildcard. Because it doesn't really matter what is here because, well, if it's an entity, it will always be true that you have 0 occurrences of whatever you're going to say. Okay, so occurrences, correctly spelled, occurrences. Let's say A, and I have this array of A, B, C. And it should be 1, right? Okay, we got an error. Okay, the error is at not, which I thought. Okay, then we cheat. We go to the solutions. We should be saying like this. Okay. Okay. For the errors. Exception. Yeah, you're saying like we got an exception there because it shouldn't be a comma. It's not a function, it's an expression. So it's saying these two are the same, nothing that. It's like saying so in other programming languages. Other like so I don't know how to actually a bar. Okay, there you go. Okay, so let's save this again and load it and call this one more time. We got true! Woo! Okay, awesome. So, like, if I do 5 and an x here, what should I get? Yeah, an array that contains 5 A's. Pretty neat. So if I run through the code again, the base case is that, well, the occurrence of something in an empty list is definitely 0. That's true. The next case is, well, if I have an x and that x is the front of the list, well, we should call ourselves again, and we should increment the parameter by 1, like this parameter by 1. Okay, but if it's not true, like this is not x, and we check it for sure here, and we're checking like the x there and the x inside the first element is not the same, then we just continue without actually counting it. Sounds straightforward. Really doable. But we're out of time. So thanks for the class. So next week will be the last lab class, so stay tuned. And I think he will post the assignment 4, which is the programming assignment in Prolog. So like look up this recording if you run into trouble. And yeah, have good luck on it. Goodbye.